Now we want to be able to put them to use. Similar to what we did with the truck problem. Okay, we want to be able to look at different situations, different phenomena, and be able to put numbers to it and equations to it, and then use quadratics to help us figure stuff out. So the lesson is actually called Quadratic Functions and Models. The only difference between those two words really is that when you start talking about a model, there is a decreased likelihood of an exact fit. When we talk about a function, it's usually a more theoretical kind of thing where here is the equation and here is the function we can get from that. It's exact, but it also is usually just sort of theoretical, like there's not any real life context to it. Once we start saying that certain things in real life look like parabolas, look like they could be quadratic in some way, chances are pretty good that what we can come up with for an equation are going to be a really good fit, but they may not be a perfect fit. Sometimes it's because even though quadratics usually have a domain of all real numbers, maybe it's only from here to here that we really can think about it as being quadratic, like the arc on our tunnel, right? Technically, that parabolic shape, that curve, did not continue on and on forever and ever. It was just from here to here. So sometimes it's because we're limited in the domain on which we can say something's quadratic. Sometimes it's because life just isn't that neat. Real life is messy sometimes and things don't fit perfectly and there's chance involved and other factors that might be involved. But we can look at a trend, we can look at the pattern overall, and it seems like the overall pattern might be quadratic, and so we can come up with a quadratic model that overall seems to fit what's going on. And it's at least a good enough fit that we can then make some predictions using it. So that's what we start talking about when we talk about models, okay, as opposed to just more theoretical functions, straight up, here's the numbers, here's the equation, we're done. So we're starting out here with questions that ask us to take bits of information about a quadratic and come up with what the equation would be. So this is more of a situation where we're coming up with a function because there's no context for these numbers at the moment. We're just being told that I know that I have a vertex here at this point. I know that I have this other point that also has to be on the parabola. What would be the equation that would make that all fit? Okay? So on this first one, looking at the fact that what we're being given is vertex and point, which of our three forms seems like the best fit to start working with? Vertex form, right? If I'm being given a vertex and a point, then vertex form seems like a great place to start. Okay? So, what's vertex form in general? A times x minus h squared, what was the rest of it? Plus k. All right. So, what's the first thing I can fill in? The vertex, and that's going to take up what pieces of my equation? H and k. So, let's see if I can just do it this way. H is going to be what? A 1. Okay, and k is going to be? So that means I should get rid of this too. Okay, -2. All right, so that got rid of some of the variables involved. I can actually put in a 1 for h, a negative 2 for k. But I still got 3 variables left. So is there anything else I could substitute in? Henry?
You could plug in the point 3 and 2. So
And where would that go?
So you plug in 3 for x and 2 for y.
So 3 for x, 2 for y. Now how many variables are we down to? 1. And the variable that's left is the a value. That a is going to tell us, with this vertex, how much does the parabola have to shrink or expand to be able to fit into this other point as well. That's why we have to have more than just the vertex to really know what the equation for parabola is, because just having the vertex doesn't tell us anything about how wide or how narrow the parabola is going to end up. Having that other point gives us an indication, and then it's the a that we have to figure out that's going to make that fit. Now, the trick here is to make sure that when you go to work this out, you follow proper order of operations. Okay? Because here's the danger. Here's what a lot of students do, and it totally messes them up. They'll go, okay, so 2 equals a times 3 minus 1 is 2. 2 squared, that's 4, minus 2. You want to take a guess?
Well, they do 2a.
They'll go, oh, okay, so that means 2 equals 2a. No! It does not. Order of operations. That 4 is being multiplied to that a, which means I cannot combine these two numbers together before I do that multiplying. So instead, this becomes 4a minus 2. And then I add the 2 over, divide by the 4, and end up with an a of 1. So once I've found the a, I then need to go back and write the final equation with x and y as variables. Okay? Because in order for me to represent all of the possible points that could be on this parabola, the x's and the y's are the ones that have to be things I can change. So x and y have to go back to being variables. H and k we're going to keep filled in with the 1 and the negative 2, and then I'm going to put in the a that I've just found. So my final answer here, let's go orange, is going to be y equals 1 x minus 1 squared minus 2.
So even if it's a 1, you still have to show it?
Yeah, okay. So if it's a 1, do we really have to show it? No. If it's anything other than 1, yes. But if 1 is the a that you get in the end, it's not necessary to write it. But some people like to just do it to kind of emphasize it in their own heads. So either way is fine. Okay, the other thing to remember is this is quadratic, which means our quantity here is being squared. That's the other very common mistake that people make, is they forget to put their square up there. And so that changes that number, which then changes the answer you get, so that messes them up too. So make sure that you square that quantity when you write out your vertex form to start plugging stuff into, so that you're actually working out the correct numbers. Okay? All right, what about the next one? This time the information I have is that I have x-intercepts at 2 and 5, and then I know that there's this other point at 4, negative 2. So which form seems like the best fit this time? What's factored form look like? Okay? So what can I fill in this time? P and Q. What's P and Q going to be? 2 and 5. 2 there and a 5 there. Okay? What else can I fill in?
Again, plug in the point.
Yeah, I've got this other point again so that I can plug in x and y. The weird thing is I'm going to plug in x twice because I have 2 different x's.
What was the x before?
So the x was 4. That's going to go here and here. And then the y of -2 goes out here. Okay, so now if we solve, -2 is going to equal a times 2 times -1, which means I end up with -2 equal to -2a, which means a is going to have to be 1 again. Now, we're starting out easy on you, okay? They're not always going to end up 1. You're going to have to work them out to find out what they really are. It's not always going to be 1. But in this case, what's our final equation going to look like? And again, with a 1 as a, you can write it or not write it. It's okay either way. Okay? Pretty simple, right? So look at the info you have, because sometimes even in an application problem, it's this kind of information you have. You may get a problem that says, a projectile was shot up into the air. We know that after, we know it hit a height after 1 second, okay, this doesn't make any sense, but you know, of -2, or after 2 seconds, we know it hit a height of 8 feet. And then at 4 seconds, we know it was down to 6 feet. So what would be the model of the path of the projectile?
You use vertex form.
Okay, so you use vertex form because they're telling you, I know that there's this particular maximum height, I know there's this other point along the way, and you use vertex form to figure out your model. Okay, or an example of intercepts might be that there's a I was trying to think, like fountain. That's the word I was looking for. It's Friday, my brain's fried. A fountain that's in the ground, right? And it's one of those fountains that just every once in a while shoots water up. Have you seen those? And so the path that the water makes is kind of a parabola. And so you might get information that says that the water is shot out of this fountain that's on the ground, and when the water shoots up, it falls so far away from the fountain. Those are x-intercepts. Like if they're talking about stuff that's happening on the ground, that's like x-intercept information. And then maybe they give you one other piece of information, like at 1 second the water is this high off the ground, and so what's the model for the problem? So you have to read, whether they're just simple problems like this or application kinds of problems, read the context to make the connections. The information they're giving me, is that like a vertex? Is that like an x-intercept? Is that like just some other point? So that you can then say, okay, so vertex form fits this best, intercept form fits this best, and then you can go from there. Set it up just like we did here. Okay? Yeah?
If you were just given the y-intercept and another point, could you use standard form?
Almost. If you are just given the y-intercept and the other point's not a vertex, you're going to need 2 other points. Okay? So if you're not given one of the specials being I get a vertex and something else, or I get both x-intercepts and something else. Okay? If you're not getting that and you're just getting 3 points, then it's going to have to be 3 points. You're not going to be able to do it with just 2. And because it's not one of the specials, what Henry says is exactly right. We're going to have to use standard form for this. Because we don't have a vertex here that we know of. I mean, there's nothing about this problem that tells us anything, any one of those is a vertex. We've got one x-intercept, but we don't know what the other one is. And there's no indication that there's only one, necessarily, like it's, the vertex itself. And so what we need to do is we need to use the standard form of y equals ax squared plus bx plus c. But what are we going to fill in? What do we have information about? Do we know anything about A or B or C? Yeah, we don't even know C in this case, right? Because we're not given a y-intercept. What we know are 3 different x's and y's that are supposed to go together. So we're going to have to set up 3 different equations for each point. So based on this first point, we would have y, whoops, don't need the y there, that's going to be 0, we know that one. So we're going to have 0 equals a times negative 1 squared plus b times negative 1 plus c. Based on the second point, we can set up negative 2 equals a times 1 squared plus b times 1 plus c. And then based on the third point, we could set up that negative 15 has to equal a times 2 squared plus b times 2 plus c. So then what do we need to do to actually figure out what a, b, and c are going to be for this equation? I've got an equation based on each of the points I was given. But now what do I do with that to find out? So what's the a, b, and c for the overall final equation? How would I do that?
You could do elimination. Like you could multiply the first 2 out, and then those 2 would, and then you can add those together, you eliminate, you get 2c, you eliminate 2.
Okay, so basically we have to solve this as a system, right? What Julian's describing here is the fact that we now have 3 equations with 3 unknowns that we would need to solve out as a system. Henry just died over there. Now, since we've already done the lesson that proves to me that you know how to do this, I'm going to let you off the hook. I'm going to show you how to do it on the calculator. I just made Henry's day. All right? So, get yourself a calculator page that you can work with. Everybody got this written down so that you can refer to it as we put stuff in? Okay, so in order to do a system of equations on your calculator, okay, you are going to start off just like you discovered in your calculator activity the other day. We want to solve something. Okay? And what's the syntax for solving? What do we have to include inside of the parentheses? what we want to solve, and then comma what we're solving for, right? So in this case, what we want to solve is not just a single equation. We want to solve an entire system. And the way to put in a system is over here beside the book. You see that where it's got the like bracket things and then the little boxes? Click on that. Beside the book. See? Yeah, beside the book. That red button up there that I pushed.
Got it.
See it? All right. There's lots of different choices here, but the one we want is this one, where we've got the bracket, and then there's 3 boxes listed there to represent 3 different equations. So click on that. And sometimes you have to click on it twice so it shows up. And they're going to ask you for that one, because it doesn't actually just represent 3. It really represents anything more than 2. So it's going to ask you, how many equations do you actually want in your system? We do just want 3, so we can just hit OK, and it looks like that. So now you need to type in your 3 different equations. So our first equation is going to end up being 0 equals 1a plus negative 1b plus c. No, it's not.
Oh, you're right, square.
No, it's not. All right, so 0 equals 1a plus a negative 1 or minus 1b plus c. And you can actually use a, b, and c. That's fine. And then either with your arrows or with your cursor, get to the second box. Second box is going to be what? Negative 2 equals a plus b plus c, right? Okay. So negative 2 equals a plus b plus c. Next box. What's my third equation going to be? Okay. Negative 15 equals 4a plus 2b plus c. Okay. Now, when you get to the end of that third equation, use your arrow, your trackpad, and arrow to the right. So you're basically getting out of the system setup. Okay, so just arrow to the right and hit your comma. And now what is it that we're trying to solve for? A, B, and C. So we're going to go A, comma, B, comma, C. And if I've told you this correctly, watch the magic work.
Too few arguments, really?
So if you're not getting answers, go back and look at how you set things up. It should look like this. What is that? That's the thing that makes your calculator not work. I gotta remember how to get you out because I haven't done this in a long time. It moves around. I don't know where it is.
I tried. I gotta be like. test where we like
Oh yeah.
when we have
That's
to
what I say.
do this the hard way or
Yeah, if you were getting something like this on a test, you would it would depend. If it was a part of a test that allowed you to use calculator, use calculator. But if not, then yes, you'd have to do it by hand. I don't know, Harry. I can't remember. I'm gonna have to ask Miss Mahoney again.
Okay. Should I go to her?
Probably not right now, because she's probably in class. But
Should I leave my calculator?
keep it for right now. Do as much as you can with it, and when answers don't come up for some reason, look on somebody else's. Oh yeah, sorry, non-cassers. Sorry.
What's the
it's a
castle?
If you don't have a CAS calculator, this isn't going to work. This is beyond what CAS will do.
Wait, actually, if it's a CS, you can't do that.
A CAS, if it's not CAS, you cannot. It won't work this out.
Resistance.
Not that I'm aware of.
By hand?
Yep. Can use the calculator to help you do it by hand, but it won't actually just do it for you. This is what CAS does. It stands for
Calculator, amazing.
Computer Algebra System. And so it's actually programmed in a different way. So like when you type something in and you hit enter and it like changes it into the form of what it should really look like rather than just, what you type horizontally. That's all part of that sort of algebra system. It'll change it into algebra stuff. And so the CAS has the capability of actually working this kind of stuff out. The non-CAS can do some minimal stuff, but not something like this complicated. Okay, so now that we have our values, now that we know that A is -4, B is -1, and C is 3, how do I give a final answer to this problem? So what is my equation that goes through those 3 points? I'll start you out. Y equals what?
Y equals -4
Plus or minus, which one? Plus 3?
Minus x plus 3.
Okay. So once you finally solve for the A, B, and the C, that has to be true in all 3 cases, then that becomes the A, B, and C in our standard form. So then we can rewrite it with the x and the y being our variables and the A, B, C being filled in. So y equals -4x squared minus x plus 3 is the equation that contains all 3 of those points. Okay? Questions on that? All right, we're going to try to do this pretty quickly here, but I think we can, if this will work. Because it's fall and there's pumpkins, so why not throw them? All right, so really quick, because we don't have a lot of time and I want to show you how to set this up. There is also a capability within your calculators, most of them, I think even the non-CASs will do this, to take data and come up with what the quadratic equation should be, okay? And here's where we get into models, because these are not going to be perfect fits, but there's a trend there that is quadratic, and so we can come up with a decent equation that represents what's going on. So here's the situation. There's a pumpkin tossing contest in Morton, Illinois every year, where people compete to see whose catapult can send pumpkins the farthest. The table shows horizontal distances the pumpkins traveled when launched at different angles. Use your Inspire to find the best fitting quadratic model for the data. So here's our table. So you know what a catapult is? Yeah, it's like when you pull it back and it's got some sort of spring action that makes it flip and throw it. Okay? So depending on the angle at which it gets thrown, it will determine how far the pumpkin's going to travel. Okay? So the first thing we need to do is get this data into our calculators. Okay? So you need to have a new page, and you need to choose lists and spreadsheets, because that's where you input data. And in your lists and spreadsheets, we are going to put in angle,
Go to your home screen.
control, doc.
New document.
It's just
If you're not in Scratchpad, go control doc. If you are in Scratchpad, go to your home screen and do a new document.
Do we type an angle?
Yeah, but we can't do angle because notice how when I start typing it's italicized, and then when I finish angle it goes regular. That means there's already something in my calculator that's programmed to be angle. So I have to call it something else, like maybe
Angles.
just ang. Just something that gives you a title up there as to what this column represents. Or angles. If that works, that's great. Or just misspell it with 2 G's. There you go. Right? So, and then the second one is going to be distance. Okay? So for angles, we had 20, 30, 40, 50, 60. 20, enter, 30, 40, 50, 60. All right, for distance, 372, 462, 372, 462, 509, 501, 509, 501, and last but not least, 437. 372, 462, 509, 501, 437. Okay, everybody got that in? All right, now add another page. So go Control, Doc to add another page. And this time we're going to choose Data and Statistics. And what you should see are just 5 random dots sitting there. But we want to see how they're related. So my x-axis down here, move your cursor down here, where it says click or enter to add variable. If you click on it, your 2 titles show up. So I want angles to be my x. I click on angles. So right now the only axis we have are angles, and we can see that there's one at 20, one at 30, one at 40, right? But now if I come over here to my y-axis and click on it and choose distance, now I can see how the 2 things are related. And you can see how there's kind of this quadratic parabola fit to it. So, in order to get the calculator to tell me what the equation for that fit should be, we're going to go Menu, Analyze, Regression. Remember linear regressions? Well, linears don't get to have all the fun. Lots of functions you can perform regressions with. So we're going to choose a quadratic regression. And so the calculator will go through very quickly the work it takes to figure out what is the best fitting parabola to the points you have. And then we'll spit out the equation that goes with it. So our equation in this case is about a y equals negative 0.26 x squared plus about 22.4x plus about 25.6. Okay? Now, let's say I want to do something with this. Let's say I want to know if I'm going to enter the pumpkin chucking contest, what is the best angle to get the maximum distance? What would I want? Give me 2 seconds. What would I want?
45. Or the the maximum, the vertex.
42.
The vertex, right? So to be able to work with this, to find something else, there's this menu, actions. Oh no, is it actions? Is it? Where is it?
Analyze.
Oh shoot, I thought it was in here. Anyway, you could take your equation from here, go to your graph page,
Graph it.
put it in, find the vertex, and then you'd know that angle is what I want to shoot it at, because that's going to give me the maximum distance.
Why?
Okay?
Everyone.
There's at least one problem, I think maybe two in your homework, where you're going to have to do that.
Oh.
Yeah.
So I apologize for being that quick, but I hope you get the idea. Basically, it's the same as linear regression, just use a quadratic. Have a good weekend, folks. We'll see you on Tuesday.